Alright, hey guys, today we're going to be solving the Australian Informatics Olympiad problem 5, which is composing pyramids. So, in the problem, there is a piano, right? And the composer has a piece named the One Finger Pianist, and his piano has 100,000 keys, numbered from 1 to 100,000, left to right. And you have to press n keys in a sequence, and the ith key is the sequence pi. In the sequence, is pi. And because you're not very skilled, you can only play musical pyramids. So it gives you the definition of musical pyramids here. So it must have an odd number of keys. It must start and finish on the same note, and it must be a sequence of ascending or descending keys up to the middle and these are all musical pyramids. Like you can see, this one starts on 1, ends on 1, it goes 1 2 3 2 1 3 4 3 1, and even just single digits are also musical pyramids. These two are not. This is an even number, you must have an odd number, and 5 6 6 5 is also an even number. So there's actually a way to get rid of the even number ones. I'll tell you how. Here we have these ones because they're not consecutive. So 1 3 5 3 1. It must be 1 2 3 2 1. Like they must go up by increments of 1. So consecutive. And these do not stop ascending or descending precisely at the middle. So 1 2 3 2 1. That's what it should be, but it's 1 2 3 4 3. And this is our input. 6 is the number of notes, and this is the sequence. And basically what we need to find is the minimum number of keys we need to remove from the sequence to make it a musical pyramid. So our solution is actually going to be a brute force solution, meaning that we find optimal solutions to the sub-problem and we join them together. So it's not the fastest, but it does get the job done, but it's a very, it's pretty long algorithm. But we do have a lot of security in our problem, meaning that not a lot can go wrong. So I'll just open up a paint tab. Let's start with our algorithm. So we'll just name our function triad, and we take in the notes, which is as I stated before, just the notes, which is these. We don't need to take in n. Alright, so we are gonna first initialize a val to be true. So this is gonna check if all of the notes are different. So 8 3 5 7 in the test case. For example, all notes are different, so we just have to convert it to a set, and if the same set length is the same as the length, then the value is true. Alright, we'll worry about this part later. So let's start. So we need 3 lists to start with: left sort, right sort, and default. So what we're going to do in our algorithm is we're going to have a 2-pointer approach. So that's our first test case. I'm just going to check it out. 2 1 3 4 2 1 2 1 3 4 2 1. Okay. So we're going to have pointer L. So we'll just call this pointer L and pointer right. And we have a default. So the default is just a default list. So notes 1 will be our right, and notes 2 will be our default, and notes is just our left. So we can call this notes 1, and notes 2 is our default. So if we're going to increment from the right, we just need to have this in reverse, and then we can use the same left sequence. So for the pointer right, the list will be a reverse list. We're not going to be operating on the same list. It's because we're going to sort the values through left and right sort. Alright, this is just a simple 2-pointer approach for the left side. So what this is going to do is, let's just remove this. So we have pointer left, right? And while left is greater than right, we're gonna increment our right and left pointers for the left sort. So we have a left pointer and a right pointer. So we check if if notes left is not equal to notes right, then we remove the notes right, and then we decrement right by 1. So we have left, and because it's not equal to right, we're going to remove this and move on to the next. And what happens if it is true? Then we move on. We increment both. We increment both, and 1 is not equal to 2, because we're always going to do left sort. And then, so we cancel out, we cancel out this, and then, so because we have 2, we've skipped over to 1 is not equal to 4, and because these two are matching in our while statement, we cross out this, and for the left sort, we're left with 2, 3, 2. So the left sort will always start on the first left pointer. And now let's go to our right sort. Our right sort is the exact same thing, just on the other side. So if we want to switch this list of numbers, oops. That's the numbers reversed, and we can do our right sort. So basically what our right sort is going to do is, let's just set this equal to 2, 3, 2. What our right sort is going to do is it's going to take this starting on 1, remember it's always going to start on 1, check if it's 2, nope, 1, yep, increment to 2 and 3, 2 and 1, 2 and 1 is not 2, we're going for the right. And because this cancels out for the while statement, we're left with 1, 3, 1. Oh, sorry. This cancels out because we're left with 1, 4, 1. If we find a match, we always leave the 2 matching pairs here because we don't want to cancel them out. It's like a palindrome. So we're left with 1, 4, 1. Okay. Now, what do we do after that? So once we've got our left and right sort algorithm, we're going to have an anomaly function. So the anomaly function is actually very interesting. We'll get back to the anomaly function later, but first we'll describe the simple algorithm. So this is a conditional to check if the triad needs anomaly sort. Else we're just going to, so if it doesn't need the anomaly sort, we're just going to oh yeah, alright. We're going to okay, sorry, just had a mind blank there. If the triad is even and sorted, we just need to remove one of the middle digits, but we don't actually need to worry about any of that now because both our triads, our sorted triads, are uneven and we don't need to remove them, and they don't have any anomalies, so we don't need to anomaly sort them. Now what we're going to do is now we've got to add an ascending and descending sort. So remember what it said before in the problem is that if we just go back, it must be ascending by consecutive digits. So 3, 4, 3, 1, 2, 3, 2, 1, right? And if you just take a look at the problem here, if you take a look at our 2, so our left sort gave us 2, 3, 2, and now right sort gave us 1, 4, 1. So if you look at the problem here, which of these two are ascending? Well, you can easily tell that this one, 2, 3, 2, is ascending. So how do we check that it's ascending? Well, first, as long as this is not 1, otherwise it's going to kind of break our algorithm. As long as the left sort or right sort is not equal to 1, we are going to arrange our notes. So first we need to check if it's going to start ascending or start descending. So if the minimum value is at the start, we know it's going to ascend. If the maximum value is at the start, we know it's going to descend. So for both of these cases, it's actually ascending. So now what do we do? If this, there's an easy way to check this actually. If the note after so we iterate over the notes, right? And if the note after our current iteration minus the current iteration node is equal to 1, then we know that it's incrementing by 1. So what I mean by this is, see, we start our iteration on 2, and what our algorithm does is we check 2 as well as 3, and then we do 3 minus 2, which is equal to 1. So that's true. That means we iterate by 1. And we keep doing this until the middle of the list, because remember, once we've sorted, it's going to be the same descending. So yeah, and for this one, right, we have 2. So this is perfect. This is a perfect example. However, for this one, we have 4 minus 1, which is equal to 3, which is not actually equal to 1, meaning it's not incrementing by 1, it's incrementing by 3. So now what do we do in this case? We remove the number afterwards, because remember, we always want to keep this number. We always want to start on this and keep it. So we remove 4, and now we've just got 1, 1. Now, once we've got 1, 1, we go back here. We go to the next step, which is, once we've done the sort, we create, and for each value we remove in our sort, we add that to our answer of deletion. So let's have a deletions. So currently equal to 1 plus our deletions before. I'll tell you how I solved that. So we've got our deletions is equal to 1 here, and we remove it through this list comprehension. So basically, we add this to a final answer. And how do we check the deletions for our previous algorithm? Like, how did it get from 232 to, how did it get from 213421 to 232? And how many deletions is that, right? So we can do this by doing this, by doing the even sort. So if we have our even sort, if nothing is even, right, then we can use a greedy approach to take the maximum length subtriad. Because remember, if you have the maximum length subtriad, right, so we have a maximum length subtriad. So 2, 1, 3, 4, 2, 1. The reason we need the maximum length is because when we minus the length of the original triad from the length of the subtriad, we want the minimum value possible, because that also means the minimum deletions. So we have the length of 6 minus 3 equals 3. So that's how many deletions we're going to have at the start. And because of our anomaly sort so we've got deletions 3, and for this one, 1, 4, 1, which is our right sort, which is also 6 minus 3 equals 3. Okay. However, what we realized with 1, 4, 1 is you need to take out the 1, which means an extra deletion. So if we keep a running sum of our deletions, our current deletions for left sort is still at 3, and our current deletions from right sort is now at 4, because we had to delete the element. And once we delete the element, it becomes 1, 1. But remember, a triad cannot be even. So we have to take one of these values out. So we use the same even sort technique. Is we take the midpoint of the midpoint of the triad, and we delete one of the midpoints, because you know they're going to be the same at the middle. So we take one of these out, and because we took one of these out, that's another deletion. We add it plus 1. As you can see, we're adding plus 1 to our final answer, giving us the right sort deletion of 5 and the left sort deletion of 3. So now basically from these two, we just have to choose the minimum. So once again, we're taking a greedy approach to this. So what is the minimum of 3 and 5? Well, it's obviously 3. So after all of our sorts and differences, the minimum answer is 3. And if we test this test case, 2, 1, 3, 4, 2, 1. Right, I'm pretty sure that's the 4, 2, 1. Right. and we run our algorithm, it should just give us an output of 3. Okay. And if we look at the sample output, we have 3 once again. Now, let's just work through all of the sub-problems first. The sample problems first. So we have 10, 11, 12, 11, 10. So first we do our right sort, left sort, and because this is a perfect triad, right? Our sort answer is always going to be at 0. Because it's a perfect triad. There's nothing to add to deletions. So remember, the running sum is just the running number of deletions. So after all of the sorts, it's going to be 0. And even at the end sort, it's also going to be 0. So our final ends is going to be 0. And we can test it out. So okay. 0. Cool. Now, let's move on to a more interesting test case, which is the sample input 3, 8, 3, 5, 7. So, if you look closely, I mentioned before that this is the 8, 3, 5, 7 test case, meaning that all of the nodes are different. And if all of the nodes are different, right, the amount of triads we can only have is 1. The maximum length of a triad we can have is 1. So basically the way we do that is we have the reason for that is 8, 3, 5. No matter what, there's no other 8, so you can't really have 1 8 at the other side, so it can't be ascending or descending. So in our left and right sort, we're just crossing because nothing matches this 8. Remember, we go for a match. If it's matched, then we move on. Otherwise, we just delete this element completely. And for our right sort, it's just 7, which is cross out 8, cross out 3, cross out 5. And so our left sort is just equal to 8, and our right sort just equal to 7. So if we have a test case like this where all of the numbers are different, all we have to do is do the length of the original algorithm, the original triad, which was 4 in this case, minus 1, because length of the original plus minus 1, which is our 3, which is how many deletions we would have. So we just do 4 minus 1. Let's say if it was 5, we had a 6 here, right? Delete that as well. 5 minus 1, which is 4. So that's gonna come in handy. So if all of the numbers are different, we set it as true, and we can use our right sort. Remember, our right sort and left sort takes the running sum of deletions, and for this test case, our running sum of deletions will be 3 for both left and right sort. And now, because it's 3, we can actually reuse this value, true. Then we just return the temporary answer of 3. And remember, we store the temporary answer after the first sort, before the ascending and descending sort, just to kind of ease it up a bit. So our running sum is going to be 3 always, and we don't need to add a ascending and descending sort since the length of the list is only 1. And the reason we have a length of nodes, you could just say, why don't we just do this, because I've got a conditional saying the length of nodes does not equal 1. That's for an anomaly, which I'll now explain. So what is an anomaly? Well, an anomaly in reference to this algorithm is basically kind of not a mistake, but a problem, right? So let's have a sort, which is 2. We'll use the first sample case. Oh wait, before that, I'll just show you the output of 8, 3, 5, 7. 8, 3, 5, 7. If we run it, we get 3. as you can see here. Now, what happens if we have an anomaly, right? So 2 1 3 4 2 1. Let's say you have 2 1 3 4 2 1. But let's say there's numbers on the other end, right? Like 7 and 6. Because of our left sort, we're just deleting numbers from the left and the right. But because these two are outliers, right? They don't fit in with the rest of the pattern, and there's only one of them, we're going to end up with our left sort just being equal to 7 and our right sort just being equal to 6, because remember, we're just going to keep crossing these out until we're just left with 7, when actually you could just cross the 7 out and then return to the right sort. So this is what I've devised a sub-algorithm called Anomaly Sort. So what does Anomaly Sort do? Let's go back to Anomaly Sort. So basically I've written here, it's just a function to remove outliers on the ends, because left and right sort does not catch them because they start on the ends. So we'll initialize a count, which is the deletions for our anomaly sorts, because remember, we need to count the deletions of the anomalies. So now we have our anomalies here. So what this very long conditional is telling us is, while nodes 2, remember that nodes 2 is our default. So nodes 2 is our default list. So it's our unaffected list by sort. So it will actually just be this, not 7 or 6 after the sort. So while the first item of nodes 2 is not equal to the last item of nodes 2, because remember, and nodes 2 and the count of nodes, the count of these are 1. So there's only one of them in the algorithm. Remember that there can only be one if they're anomalies, because they're not on the other side, and then there's no other side to match them with, because it has to be even on both sides. So while these two are not equal to each other and there's only one of these, we increment count by 1, which means we increment our deletions by 1, and we remove our anomalies like this and like this, and then we move on to the next one. So these two are not equal to each other. However, there is more than one of these in the triad, so we stop there. And this works for any amount of anomalies on the end. So let's say we have 9, 8, 2, 1, 3, 4, 2, 1, 6, 7. Right, these two are not equal, there's one of them. These two are not equal, there's one of them. These two are not equal, but there is 2 of them, so we leave it here. And boom, it returns us our sorted triad through anomaly sort, of course. And basically we just have to, after this, right, because the anomaly sort is after our algorithm here, we can just sort it through again. Of course we can place anomaly sort before our algorithm, but that would be slightly more confusing. Now we have this conditional to check if the triad needs anomaly sort. So if the triad meets these conditions, which is basically just our first conditional, right? If nodes 1 is not equal to the same, because remember, after left and right sort, let's go back to our left and right sort again of this algorithm. Let's say we had 7 and 6s on the end, right? So our left sort would be 7 and our right sort would be 6. So they're both 1 digit. So while this is not equal to this, so remember nodes 1 is right sort and nodes is left sort. So while this is not equal to this, and the counts of these in the default triad is 1, remember, because we can only have one instance of them, and val equals false. Remember what we set val to here, if all of these are different, and after we sorted them, you would either end up with either 8 or 7. However, in this case, val is false because these two these two are outliers and not like this test case. If you want, you can go back to the test case I explained before. So, and while val is false, then we run the anomaly sort on the algorithm, and we then store our running sum into a temp. We store our running sum into temp. So after it sorts the algorithm, then we rerun the right sort. Actually, we only need to run one of them, and we just have to remove the anomalies. If we go to if we go here and we see our right sort, and we check down here to the what's it called? Oh yeah, sorry. We check down here to our temp list for sort. We see we're incrementing count. We're timesing count by 2, and the reason we're timesing count by 2 is for each anomaly sort, right? It removes it on just the end, and the reason because it removes it on just the ends. There's two ends, so we need to have 2. The reason I've set it to 1 just in case there's a problem and we can't remove it by 1. Now, we go to our next part of the algorithm, which is just sorting if it's even or odd, and then we can go past. And once we've got our final sorted algorithm, we've got our final answer, and then if it's sorted again, we can even it out, and we return final. So I'll just show you here what it looks like. And if we go back here, we've put in 6 and 7, right, as our anomalies on the base. And now what we can do is see that our answer is 5. And the reason our answer is 5 is because, remember, with this same algorithm, after it's sorted, the minimum answer you could get was 3. But because we have 2 anomalies, we have to cross them out as well. And that just adds 2 more deletions, giving us the answer of 5. So now we have 1 deletion. One anomaly on one end. And you're probably wondering why, and as you can see, it increments to 4. However, it de-increments to 4 because we just need 1, and then we've got the full sort. Now, you're probably wondering the reason why it's 4 is because our algorithm, why we don't need to do do we need to do the anomaly sort? And we don't, because remember, with our sorts we have left and right sort. However, with our left and right sort, we can get our left sort gives us, our right sort gives us 2, 3, 2 once again, but with 4 deletions, and this gives us 1, 4, 1 with 4 deletions. But remember, after 1, 4, 1, we need to delete the 4, which gives us 5, and delete the 1 to make it odd, which gives us 6. And we can just take the minimum, which is 4. So that's our 4. And that's why we don't need to do anomaly sort, because we've got 2 pointers to sort out if the anomaly is just on one side, which actually makes it really, really helpful, because we don't have to rerun the anomaly sort algorithm. And basically, that is just how to solve the composing pyramids triad. We've gone through all of the test cases, and you can see that this, we take the minimum number of deletions by doing a left and right sort, and then optimizing both sorts and seeing which one has the minimum number of deletions. This one will always have 0 no matter what, no matter how long it is, no matter how long it is, it will always be 0. And this one, we've set a value for specific test cases just like this. And if there's anomalies on the end, we've sorted for that as well. And that is why it's a brute force algorithm, because we've kind of split it into the sub-problems, the same sub-problems that the sample inputs give us, as well as our own anomalies. And that gives us the best output, not the best time, but the safest and most reliable output, and less chance of breaking our algorithm with weird inputs. And that is basically the AIO problem 5 finished. So I hope you enjoyed. Thank you.